All right, let's dive right into this explainer. Welcome to your foundational board review on clinical optics. I'm your host, and today we are going to build your absolute mastery of the Vergence formula from the ground up. Listen, we aren't just going to blindly memorize equations for a test today. We are going to fundamentally understand what light is doing, why it's doing it, and exactly how you're going to use that knowledge tomorrow in the OR to calculate an IOL power for a cataract patient, or in the clinic to prescribe a high-plus lens for an aphakic child. Here's our study plan for mastering Vergence before the OCAPs. We'll methodically progress from core definitions to solving single and multi-lens systems. We'll unveil the convenient fiction of optical drawings. And finally, we're going to shift our mental model entirely to understand lenses as stacked prisms. Let's get to it. Okay, Section 1. Let's start with the absolute bedrock of optics, describing the relationship among light rays before, during, and after they hit a refractive surface. This formula right here is your absolute best friend. U plus P equals V. Everything is measured in diopters. And here's a great little mnemonic to lock it in forever. U is the incoming Vergence. It's what the universe gives you. P is the dioptric power. It's what the piece of glass does. And V is the resulting Vergence, the visual result leaving the lens. Master this now because I promise you, we are going to use this exact same formula for mirrors later in your optical training. Okay, grab your pens because here is a massive OCAP pearl right off the bat. The Vergence of converging rays is always positive. The Vergence of diverging rays is always negative. No exceptions. Furthermore, any distance to the left of the lens is considered minus, and any distance to the right is plus. Why is left minus? Well, because in optics, we conventionally assume light naturally travels from left to right. So anything working against that forward flow is naturally negative. Do not confuse these signs on test day, or honestly, your entire mathematical foundation is going to crumble before you even solve the very first step. Moving right along to Section 2. Now, what's really interesting here is how we translate those abstract diopters back into real-world physical space. You know, the actual distances you'll be measuring in the exam room. To move between Vergence and distance, you simply take the reciprocal. It's that easy. The distance of the final image is 1 divided by V. The Vergence of incoming light, our U, is 1 divided by the distance from its source. And here's a classic board setup for you. What if the incoming rays are perfectly parallel? Think about that for a second. Well, if they're parallel, they have absolutely zero Vergence, so U equals 0. So if you have a +1 diopter lens and parallel incoming rays, your V is simply +1, meaning your focal distance is 1 divided by 1, which equals exactly 1 meter to the right of the lens. Section 3. We've seen single lenses, but the examiners absolutely love to test your clinical reasoning by stacking them. This is exactly where we separate surface-level memorization from true long-term mastery. Here is a classic board question that literally trips up half the residents every single year. Take a moment and just mentally think through how you would set up this math before I reveal the trick. You have an object sitting half a meter left of a +4 lens, and then a whole meter behind that is a +3 lens. How on earth do we find the final image? The secret here isn't some complex new formula. It's just a simple algorithm. You do not try to solve both lenses at once. Instead, isolate the first lens. Solve U plus P equals V. Now, take the image you just found and pretend it's the brand new physical object for the second lens. Then just run U plus P equals V all over again for that second lens. You just loop this algorithm and it works perfectly for literally any number of lenses they try to throw at you. Let's look at a harder example to prove this works, and let's trace this directly together. Look at the column for lens 1. Our incoming Vergence, U, is -2. Remember, that's 1 divided by -0.5. Drop down a row, our P is -2. Now the next row, our V is -4. Look at the bottom row for lens 1. That places our first image 0.25 meters to the left of the first lens. Now move over to the top of the lens 2 column. This right here is the magic step. That image from lens 1 is now our new object. Since it's 0.25 meters left of lens 1, and lens 2 is another 1 meter to the right of that, our new starting distance for lens 2 is -1.25 meters. Run the math for U. 1 divided by -1.25 gives an incoming Vergence of -0.8 diopters. Add the +1 diopter lens power in the next row down, and our final V is +0.2 diopters. And finally, 1 divided by 0.2 gives us a final image exactly 5 meters to the right of lens 2. The total distance from the original object, 6.5 meters. Beautiful, right? All right, section 4. That last problem brilliantly illustrates something truly profound about what we're actually doing when we chart these light paths. This is where the theory meets our reality. As you're attending, I really need you to realize a secret that confuses a ton of residents. When we solved that last problem, the image from the first lens formed to the left of the lens. Now, does the light actually bounce backwards through the lens to get there? No, of course not. After light passes through a minus lens, it just acts as if it came from that location, but it isn't physically traveling backwards. Clinical optics is a convenient fiction. It's a mathematical metaphor that allows us to confidently prescribe real, life-changing vision for our patients. Because it's a metaphor, there are some really common board traps you've got to avoid. First, do not assume rays literally pass backwards through a lens. Second, if a drawing shows highly divergent rays coming out of lens 1, don't be fooled into thinking they miss lens 2 entirely just because of how the illustrator happened to draw it. In reality, some light will always make it through. When you look at a 2D AuCap drawing, always look for those dashed lines. That's just the illustrator bailing out the math to artificially extend the boundaries of the second lens just to capture those rays. Don't let 2D drawing artifacts trick your clinical judgment. Section 5. Let's see how all of this builds our understanding of what a diopter physically represents. We're going to shift our mental model entirely over to prisms. Before we talk about lenses again, recall what a prism diopter actually is. A single prism diopter displaces light exactly 1 centimeter at a distance of 1 meter. This is exactly why we use prisms to measure strabismus deviations in the clinic. We're literally measuring how many centimeters the image is displaced on the retina. Notice how this sounds remarkably similar to a lens diopter, which focuses light over the course of a meter? But here's a critical distinction. Do not confuse prisms with lenses in isolation. Prisms do not induce vergence. They only change the direction of the light rays. A prism alone will not converge or diverge your parallel rays. It's just going to bend the whole beam somewhere else. However, if we take 2 prisms and stack them base to base, what happens? Well, the top prism bends light down. The bottom prism bends light up. Boom, we've just built a plus lens that converges light. Conversely, if we stack them apex to apex, they bend light away from the center, building a minus lens that diverges light. Thinking of all lenses as stacked prisms is honestly the ultimate hack for understanding complex optical behaviors. Finally, section 6. Because lenses are essentially stacked prisms, they inherit all the physical quirks of a prism, and that leads us to a massive clinical takeaway regarding visual pathology. So, we know that a glass prism disperses white light into a rainbow, right? It does this because different wavelengths of color are refracted by different amounts. Shorter wavelengths bend more. Now, since we just established that lenses are composed of prisms, it logically follows that lenses must disperse light too. This creates chromatic aberration. And this isn't just trivia. It is the entire basis for the red-green duochrome test you use during refraction. Shorter green wavelengths focus in front of longer red ones. If the letters on the red side are clearer, the image is too far back and you need to add more minus. RAM gap. Red add minus, green add plus. We have covered a ton of ground today. From the absolutely unbreakable U plus P equals V formula, to looping multiple lenses, to recognizing the convenient fiction of optical diagrams, and finally seeing lenses as stacked prisms. So here is my final challenge to you. If clinical optics is just a mathematical metaphor, how are you going to use this framework tomorrow morning to give a patient the gift of clear sight? Understand the math? Master this mental model, avoid those traps we talked about, and I promise you, you are more than ready for both the OCAPs and the clinic. Thanks for learning with me today.